John McDonald is the smart grid business development leader for GE's Grid Solutions business. He has 46 years of experience in utility industry. He has extensively worked in different IEEE standards and also in committees. He has received multiple honors. Specifically, he has been awarded a Life Fellow of IEEE member for 49 years, and he was, as he was mentioning, next year would be his 50th year or Golden Jubilee celebration in IEEE. He was also awarded the IEEE Millennium Medal in 2000, IEEE PES Excellence in Power Distribution Engineering Award in 2002, the IEEE PES Substations Committee Distinguished Service Award in 2003, the IEEE PES Meritorious Service Award in 2015, the 2016 Degree Distinguished Member Award, and 2016 Degree UNSC Atwood Associate Award. He has co-authored 5 books and has 1 US patent. And with such a distinguished career that John has had, I think we are happy to host him in our first lecture series here. Over to you, John. Thank you, and over to you.
Okay, good. Can you, I just wanted to check, can you still hear me okay?
Yep, we can hear you okay. This is just everyone joining in. Please mute as you join in. The way we would go ahead with questions during our meeting today would be to fill in the chat window with questions, and when you're typing in the questions, please address it to Mustaq or Rafael in the 2 column that would be noticed when you're trying to type in the chat. Thank you, everyone, and over to John, to you.
Yeah, I look forward to questions too, because when I'm involved in panel sessions. Hey, could everyone please go on mute? Please put your laptops or your phones on mute. But I find the feedback I get when I moderate a panel session or speak at a panel session at like an IEEE meeting, the audience, they say, you know, I learned more from the questions and the interaction afterwards than I did from the prepared talks themselves. So please, you know, as we go through the material, if you have a question, jot it down or remember it, and we'll have plenty of time afterwards to go through the questions. So you know, in the industry, we started with the term smart grid. Smart grid became, really, it didn't really have any impact anymore because it seemed like everything that we were doing and talking about was all part of smart grid. So we're using the term grid modernization, which I really like. It's actionable. You know, we're modernizing the grid, and it, to me, it has more impact. We're using that, even the Department of Energy in the US is using that term now. And I call this technological advancements beyond smart grid. In other words, what do we need to, not so much what we've been doing, but what do we need to do for the future? Okay. And I have been involved quite a bit with IEEE Power and Energy Society, and also with IEEE Standards Association over the years. Yeah, next year will be my 50th year of membership in IEEE. I've also been very involved with CGRAE. CGRAE is organized by National Committee. The U.S. National Committee is the 2nd largest globally of CGRAE, and I've been running the technical activities of the U.S. CGRAE for over 10 years, about 14 years now. A little bit more. I think what's important, a couple things that are important that many people may not know about me, is that I mentor many young professionals, and I find that as all of us, as you get older, your focus should be on sharing your background and experience to help others be successful themselves. And that's very important to me. I don't need any awards or recognition anymore. I've had plenty of that over my career. what I love to do now is to help other people be successful themselves. That's the greatest feeling in the world, when I see someone that I've had been helping be successful themselves. Also very involved with Boy Scouts. I'm an Eagle Scout. My son's an Eagle Scout, and was on the board of the Atlanta Boy Scouts for 8 years. For 6 years, I had an Explorer post at GE, which was, I had 40 high school boys and girls that came to GE one night a month, and I did different programs on STEM, science, technology, engineering, and math, to help both boys and girls in high school really figure out what they may want to do, what they may want to study at the university, and maybe work later on. I've been married 40 years, 2 children, 2 grandchildren. My daughter's 39 and teaches autistic children. She's been teaching special needs kids for over 17 years. My son is 35, went to Georgia Tech, electrical engineer, specialized in power, worked for GE for 4.5 years doing power system studies, got his MBA at Duke University, like I got my MBA at Berkeley, and went into energy finance, the finance side of energy, became an investment banker. He now works on the finance side of energy. My wife, the 12 years I was on the IEEE Power and Energy Society Governing Board, we had 4 board meetings each year. So my wife went with me to like 48 different IEEE PS board meetings all over the world over 12 years. And I say that my wife knows more about the Power and Energy Society than most members do. She didn't want to, but by being with me for all those board meetings and all the dinners and talking with people, she learned a lot about society. Last thing is, as you get older, well, no matter what age you are, but particularly as you get older, you really got to take good care of yourself. I have over 4 million miles on Delta, always do a lot of traveling. And to keep the schedule that I keep, I need to be in good shape. So for 10 years now, I've been working out with a personal trainer. See a photo on the lower right, who was a professional football player. We played wide receiver for Georgia Tech, and then he played for the Chicago Bears and the Atlanta Falcons. One of my best friends. We compete with each other with 5K races, and just enjoy working out a lot. And then I like to run 5K races. And top right is my son, the day after his graduation with his MBA at Duke. There's a famous 5K trail at Duke University called the Al Bueller Trail. And we had just finished running that trail. So if you're interested in protection, automation, and control, you really, if you haven't already, you should subscribe to PAC World Magazine. PAC, capital letters, Protection, Automation, Control. PAC World Magazine comes out every quarter. The September issue last year featured my personal story of my exercise in the hobby section of the issue. Okay, and next month, the June issue, if you know the magazine, you know every issue features an industry guru and talks about the life story of this person, how they got involved in protection, automation, control, and has a lot of photos and really the very personal story of this person. I'm very fortunate. I'll be featured as the guru in the June issue of PAC World Magazine. So you'll see my photo on the front cover and a lot of information about my life inside. So you really want to make sure that you have a balanced life, work-life balance, but also your personal health. Work is important, but God gave us all one body. We typically have multiple jobs in our career. You can't trade in your body for another one. You got to take good care of it. And it's very important to do that, especially as you get older. These are the things I want to cover with grid modernization. And it'll be a good comprehensive overview of the entire grid. and again, what we're looking for the future, okay? So the first thing I always say is need to know what's happening in the world around us, key industry, societal trends. If you don't know what's happening in the world around you, the risk is that you make a decision for your company or for yourself or for your organization that may not be the best decision. You think it's the best decision, but something may be happening in the world around you that impacts that and you just aren't aware of it. A good example is a new industry standard is being developed that will have a new communications protocol for, say, substation automation. And you're not involved in it, you don't know about it, you're developing product or buying product from a vendor to use, and all of a sudden the standards published after you have the product, and 6-9 months later what you just bought is obsolete because it doesn't use this new protocol. You really have to know what's happening in the world around you. So you really have to have a balance between internal focus, your work, and external focus, getting involved in IEEE, PES, getting involved like I did back in 1987. I got involved with writing standards for substations and particularly substation automation, and then eventually became chair of the substations committee. You really need to know what's happening. So the first thing is we've transitioned from devices and systems to holistic solutions. The intelligent electronic device, the microprocessor-based device, has two-way communications. So we look for opportunities to have that as a node in a network, okay? So the relay has value to the utility, but when that relay is used in a substation automation system, for example, or a special protection scheme, or something that's greater, an integrated solution, that integrated solution has much more value to the utility. So devices and systems are good, but the holistic solution is what we really want to strive for. And that's why we always have to think of the big picture, okay? Don't just get hung up on the component, but think about the big picture. And the word holistic is important here. Holistic means company-wide or enterprise-wide. I don't want to just optimize the maintenance group of the utility or the planning group or the engineering group or the power quality group. I want to have the needs of every single group in the utility, and any new technology or any new solution that I propose, I want to make sure it satisfies as many needs of the entire utility as possible. We have to break down the silos of the individual groups and think company-wide, think holistic. So I'm going to show you in a minute here 6 holistic solutions that have the strongest business case for electric utilities today and in the future. Second thing is success is more than just technology, okay? It's industry standards and policy. This is a 3-legged stool. Each leg is strong, has to be strong. Each leg is just as important as the other. If one of these 3 legs is missing, you try to sit down on a stool, it's going to fall over, right? It's not going to work. It's not going to be successful. So, in addition to technology today, industry standards are extremely important, because without compliance to standards, we can't have components that are interoperable with each other. The 2 key words today are integration and interoperability. And I could have the best technology in the world that interoperates, but if policy doesn't incentivize the customer to buy my technology, no matter how good it is, I may never make a sale. Okay, so we spend a lot of time, policymakers shaping policy, both in the United States at the state level, which is complex because it's 51 different public service commissions, the 50 states and the District of Columbia. But it's important because they govern the distribution part of the grid and the end use customer part of the grid. Okay, and we also spend time nationally with FERC and NERC, who govern generation and transmission. Okay, grid flexibility. We're always looking at how can we add logic on the grid, but also close the loop on that logic so our grid is self-healing as much as possible. You know, I mean, I can put logic on a distribution system today that can detect the fault, locate the fault, isolate the fault, and do both upstream and downstream restoration within a minute or two automatically with no human in the loop. You know, truly a self-healing grid. Also, in addition to that, resiliency of the grid is really important. You know, 3 or 4 years ago at GE, we hired Gallup, the professional polling company, to help us do a poll of thousands of utility customers in the US. And one of the questions we asked was, how many of you would be willing to pay $10 or more extra on your electric bill per month if all the extra money went to making the grid more resilient? And to an end use customer, more resilient means, you know, lesser outages, and when there is an outage, a shorter outage, right? What was amazing to us was for those customers east in the eastern part of the United States, 41% said they would do this, and 34% in the western part of the US. We knew there would be that difference because the customers in the eastern part of the US have experienced 3 times the outages than those in the west, okay? But it shows you how important resiliency is to customers. Because of that, electric utilities today, one of the impacts is you're seeing much more emphasis on microgrids, right? When microgrids first started, we saw those as a very niche technology. By niche, I mean 3 specific applications only. One was university campuses. All the universities were looking at better energy efficiency throughout their campus, so we saw microgrids being used. Second was military bases. You know, there was a lot of emphasis on military bases being more resilient and also using more renewable energy. And then third is rural villages. At GE, our first microgrid project was a rural village in British Columbia, Canada, called Bella Coola. I'll show you the one-line diagram of that microgrid a little later on. But today it's very different. We see utilities looking at microgrids to improve the resiliency of their grid. Instead of having one heterogeneous grid, let's subdivide the larger grid into some strategic microgrids that have enough generation that they can operate islanded, right? So if there's a problem in other parts of the grid, right, we can island the grid and still continue operation. So we see, Commonwealth Edison is a good example. I think they're putting in 5 microgrids now from the point of view of resiliency. So there's a lot of emphasis now on resiliency, and particularly one of the impacts of that is much more use of microgrids. We will talk about big data. That's a whole different topic in itself that I love to talk about, and I have a number of articles and papers I've done on big data. One of the 5 books I've co-authored is a book called Big Data Application in Power Systems. We just published that in 2018, and I wrote the first chapter in that book called A Holistic Approach to Becoming a Data-Driven Utility. Okay, this is a whole topic unto itself. I'm going to touch on this later on. Use of the cloud for automation applications today. There's cloud components in all automation system applications. And use of social media. We're emphasizing the use of social media much more by utilities. I wrote an article 4, 5, 6 years ago called How We Can Use Social Media to Accelerate the Restoration of Electricity After an Outage. And I talked about intelligently parsing tweet information from customers, which we've done at GE, and we can put that information, that outage information from the tweet directly into the outage management system without any person involved in the loop, okay? You know, there's a lot of benefits here to using social media. On that poll we did with Gallup, another question we asked of customers was, what is your preferred way to interact with your utility? You know, telephone, social media, you know, in person at a branch office, you know, and 70% of the customers said social media. Okay, so this is the way customers want to interact. We need to you know, use this to a greater extent. And then lastly is what's really important is the convergence of IT and OT to support enterprise data management. IT is the information technology side of the utility, and OT is the operation side. Early on in smart grid, going back 10, 12 years, I remember in the industry with IEEE and C-grade, we asked the Chinese, you know, hey, what are your plans for smart grid? You know, here's a country growing like mad, and with a lot of focus on more generation transmission because of the huge growth. And you know, the response was very profound, and I'll never forget it. It was, you know, before we think about smart grid, we need to make sure we have a strong grid. Strong grid before smart grid. And that's so true. In my 46-year career, about a third of that has been doing international consulting for electric utilities. And the other 2/3 is working with 4 different automation system suppliers. But as a consultant, you know, the utility would hire me and say, John, we have, you know, we want to implement this new and this new and this new. And I said, well, wait a minute, let's take a look at 2 things first, your communications infrastructure and your IT infrastructure. Because if your communications infrastructure isn't robust enough holistically, right, enterprise wide, we may be adding a bunch of new stuff here, and you may not get the performance you expect because the underlying foundation has weak spots, right? And those weak spots could be communications infrastructure, or it could be the IT infrastructure. The IT infrastructure helps us with enterprise data management, getting, you know, bringing important data from the operations side over to the corporate side, okay? We're going to talk more about that also. So let's look at smart grid concepts first. And I want to emphasize a little bit more about the IT-OT convergence, bringing together the electrical and the information infrastructures. The 4 things that these comprehensive solutions provide us is improving the reliability, performance, and productivity of the grid, increases in energy efficiency and decreases in carbon emissions. So, you know, we're showing here the environmental benefits of smart grid. But these last 2 were fairly new for us with smart grid. You know, one is empowering customers, consumers, to manage their energy use and save money, but without compromising their lifestyle. This is giving the end use consumer the technology and the tools where they can manage their energy use themselves. You know, this gets into possibly Alexa, right? In what we call in-home enabling technology, and the ability to cut maybe 20, 25% or more off of your monthly electric bill. And the other one is, last bullet, optimize renewable energy integration and enable broader penetration. And we'll talk a lot more about that. End result is deliver meaningful, measurable, and sustainable benefits to the utility, the consumer, the economy, and the environment. But I think the best end result of what we're doing in the last 10, 12 years with what we call smart grid is much more focus on the distribution system. I've been involved with electric utilities for 46 years, and for many of those years, most of the investment was in generation transmission. It was very difficult for the distribution folks at the utility to get much budget money for investment. And that's why today in the United States, we have 52,000 distribution substations, and only 2/3 of those have any automation installed today. So, think about that. 1/3 of our distribution substations are unobservable at the control center. So this is why we really needed much more focus on distribution. And I'm gonna talk a lot about different aspects of the distribution system in this talk. Okay? Now, you can imagine, when this whole thing about smart grid first came up, a lot of folks like myself who had been in the industry for many years. I mean, I've been adding intelligence to the grid since the mid 70s, right, with my work. So this thing about smart grid was not new, for many of us that have been involved like in IEEE for many years and writing standards and stuff. We're saying, wait a minute, we've been adding intelligence to the grid for a long time. So I said, I need to put this slide together here and really call it not smart grid, but a smarter grid. And I need to differentiate what we've been doing for not only years, but decades, and that's shaded in light gray. And then what are the new things that we're doing, which is in light green, okay? Because let's acknowledge the fact that, we've been adding intelligence to the grid for a long time. So given that, what is it that we're doing new? Well, if you look at the bottom, you can see I've shaded halfway voltage control. Voltage control, half of it is light gray and half of it is light green. I mean, we've been doing voltage control for years. I mean, I was doing it in the 1970s, particularly for electric co-op utilities, to prevent them from exceeding their previous peak, because voltage is directly proportional to load. And if I can lower the voltage on the distribution system, I can lower the load. So, we've been doing that for a long time. But now what we're doing new is integrating voltage control with VAR control, with reactive power control. So we call it today integrated volt-VAR control. VAR is directly proportional to losses, reducing losses, voltage, and load. Turns out if I do them separate, they can tend to buck each other, the control, and I to some extent negate the benefits of one over the other. Okay, so it's important to coordinate them to optimize the coordinated operation. On the right side, renewable generation, we'll talk more about that. If I go in the middle, sensors, again, that's half shaded in light green. We've been adding sensors to the grid, but there's much more emphasis on that because there are areas, particularly of distribution, that are unobservable. We don't have any automation installed. We don't know what's happening. Okay. We also have more specialized sensors today that we're adding to the grid. This one here that I'm showing is a monitoring and diagnostic sensor that I would add to a transformer, and the oil from the main tank of the transformer would flow through that sensor. This particular one can detect up to 2 gases dissolved in the oil of the main tank, but I could replace that with a sensor that could detect up to 9 different gases that are dissolved in the oil of the main tank. So I can tailor the amount of money I spend on monitoring diagnostics with assets based on the criticality of that asset. Okay, so doing a lot more with sensors. Here's the distribution management. That's next to sensors. That's the advanced distribution management system, the new distribution SCADA that we're putting in. Next is distribution automation, which we'll talk a lot about, the feeder automation downstream of the substations. And we'll also talk about advanced smart meters and the additional data we can get from smart meters over and above just the usage information. The top of this are the are the solutions, the integrated solutions that we'll talk about on the next couple slides. So again, I said the concept of holistic solutions was an important concept. These are 6 holistic solutions here that have strong business cases for electric utilities. And we're transitioning, as I said, from products and systems to holistic solutions. First is asset optimization. We started with a focus on transformers because the average age of a transformer in the US is over 42 years old, okay? And this is not just a US issue, but in the UK, it's close to 40 years old. So this is, true around the world. The other thing is the cost of a transformer could be well over $1 million or several $1 million. So a relatively small investment in monitoring and diagnostic equipment can not only save the life of the transformer, but extend the life of the transformer, right? And I can show you, if I do the business case of that, if I can save the life of $1 million transformer by 2 years, in other words, delay the replacement by 2 years, on that business case, I've saved the utility $100,000. In other words, it's about a 10% savings to the utility just by delaying the replacement by 2 years. Okay, so this is a strong business case here. Now we've moved from transformers to high voltage and medium voltage switchgear. We're looking at optimization and monitoring diagnostics of not just transformers, but switchgear, circuit breakers also. Demand optimization, is very important. We're aggregating controllable load, controllable customer load, and using it now as a dispatch tool in the control center. So instead of just doing automatic generation control, and when load increases and frequency drops, I ramp generating units that are on regulation. It may be less expensive for me to pull the trigger on some aggregated load through demand optimization. Okay, again, a dispatch tool in the control center. Third is smart metering and communications. 50 million smart meters now installed in the US. And I'm going to show you how important a smart meter is with respect to the information it can provide us. Okay. Fourth is distribution optimization. This today has the most activity, this holistic solution, and the strongest business cases for utilities. Fifth, and we'll talk a lot more about this. Fifth is transmission optimization. One of the things that we have been focused on with transmission is greater use of the information from synchrophasers, right? When you can get information 40 to 50 samples per second, as opposed to SCADA data, which is every 2 to 4 seconds, you have so much more insight into what's happening on the grid. And we first brought that synchrophaser information into the EMS, into the SCADA system for generation transmission, to help us with the state estimator application. But now, there's wide area measurement systems, and there's so much more we can do with synchrophasers. We've just really touched the tip of the iceberg with the value. And then lastly is workforce and engineering design optimization. Within the next 5 years in the US, 40% of the employees in energy today and 60% of the executives all will retire. Think about that. 40% of the employees, not just engineers, but employees, and 60% of the executives will retire. So focusing on the workforce, how do we attract young people? How do we retain young people, right? How do we transition and convey all the information from the senior experienced people to the young people? There's a lot of workforce issues we're dealing with. In fact, I'm one of 3 instructors on Thursday this week. In 2 days, and we're teaching a virtual workforce course. In fact, the title of the course is Changing Workforce for Utilities, offered by EUCI. It's a virtual course. So there's a lot of emphasis on the workforce today. You know, this, in fact, the emphasis on the workforce was the reason we changed the name of the Power Engineering Society in 2008. We changed it from IEEE. It's always PES, but we changed it from the Power Engineering Society to the Power and Energy Society in 2008. I was the IEEE PS president in 2006 and 7. And so it was during that time we surveyed university students. We found out, you know, what do we need to do to attract young people to the society? And having the word energy in our name was huge. We've had tremendous growth since then, and we're now the second largest society in all IEEE with over 40,000 members. So if we take these 6 solutions and we color code these and show the components of these solutions, this is the technology roadmap. And I like to do this because this is what I mean by a holistic solution across the entire enterprise. And you can see all the different components here from different vendors that all have to be integrated together to work together. They have to interoperate. And this isn't trivial. And this is why I emphasize the need and how important industry standards are. Let's just take a look at the light blue boxes. In the upper left, you have the office and the control center. In the top 4 light blue boxes are software applications that run on the distribution management system. Below that, the DMS, distribution management system, outage management system, these are systems. We go down to the substation and we see relays, we see the station controller, we call it data concentrator. We see applications now, not just running in the control center, but we see applications running at the substation level. We've distributed the intelligence. These are VOLVAR control, fault detection, isolation, restoration. We can run at the substation level. Then to the right and the bottom, we see switches and breakers. We need switches on the feeders to support the fault detection, isolation, and restoration logic. And we need capacitor banks and voltage regulators on the feeders to support the integrated VOLVAR control logic. Again, the logic could be at the control center or it could be running in the substation. But this is what I mean by a holistic solution, technology components from different vendors integrated together to successfully interoperate to meet the business needs of the utility. Okay. So when a utility buys a new ADMS, Advanced Distribution Management System, which is, we call that today, instead of DMS or Distribution Management System, if the project is done right, 30% of the total project cost is the cost of the DMS from the vendor, and 70% is the cost to integrate that with other systems and devices in the enterprise. Okay, integration is key to success. So here we're showing not only using the meter readings from smart meters, but the voltage from certain meters at the ends of certain feeders that go into the network model and the distribution management system. We need that for VOLVAR control. And also, when there's an outage, we get a last gasp communication from the smart meter, which we send directly into the outage management system. The GIS, the Geographic Information System, is the reference system for the network model for the outage management system and the distribution management system. We send status changes from the distribution management system to the outage management system. Think about it, if a feeder breaker trips in distribution, that one status change, sending it to the OMS with its network model, it knows each customer and how that customer is electrically connected to the grid. So if the OMS knows, hey, this feeder breaker tripped, now this feeder is de-energized, it knows all the customers that have outage now, whether you have smart meters or not, right? And then previously we talked about how important social media is. We move customers from using phone calls, right, to communicate outage information or to communicate with the utility to social media. So we can integrate distributed generation into the grid, either transmission level, distribution level, or the end user level. The challenge here with distribution is that we designed a distribution system to have electricity flowing in one direction, source to load. And we set our protective relays that way, really assuming that we'd have flow from source to load only. Now with distributed generation, we have electricity flowing in two directions. We integrate renewables, distributed generation along the distribution system. When a fault occurs, we could have a load side contribution now to the fault. So what are some of the challenges? Well, one is open circuit over voltage, unintentional islanding. Two would be protection ratings that may not match fault currents. When we set the relays, we did a short circuit study, but we only looked at the source side contribution to the fault. Now as the penetration of distributed generation grows, we have a load side contribution. So our protection rating may not have taken that into account, right? But next is we have varying fault currents due to the distributed generation. That load side contribution is not constant, it varies because of the intermittency of the distributed generation. The sun isn't shining all the time, the wind's not blowing all the time. So how do we set the protection relays? What's the proper settings with a significant amount of load side contribution? And I'll talk more about the stress on the voltage regulation equipment. So this is the first microgrid project we did at GE. This is Bella Coola rural village in British Columbia, and not near any utility. So it had its own diesel generation. That was its base generation. Had both industrial and residential load. Had fuel cells, hydrogen fuel cells, some PV panels for solar generation, and some low had hydro. So we took a microprocessor-based relay and made it into a microgrid controller by adding logic to it. And so it would make sure the load was satisfied all the time, but optimize the use of the fuel cells, the solar generation, and the hydro generation, and minimize the use of the diesel generation. And then in Philadelphia, another example of microgrids is what used to be the Navy Yard, where naval ships were repaired and worked on, and now that's become a industrial development site. And the Philadelphia Industrial Development Corporation is now encouraging economic development of that site. And we've added a couple microgrids to that site by working with PJM, the independent system operator there, and PECO, right, Philadelphia Electric Company, one of the Exelon companies there, the utilities. Now, there's been tremendous growth. So through some money from Department of Energy, as well as some other relationships, Penn State University and the Burns Group, we actually added, in addition to the microgrids, a microgrid control center with a DMS, distribution management system. Also, the folks there use the open source 3-phase load flow software called GridLab-D, which is developed by one of the Department of Energy labs, the Pacific Northwest National Lab, PNNL, okay? And then we've added a microgrid automation control system at each of the microgrids, which is based on ANSI standards as well as the IEEE standard 1547. which is the standard for the rules to integrate distributed generation with the electric grid. Okay. So there's challenges with renewable generation, right? With the intermittency. There's some solutions also. We have very fast start thermal generation today that's designed to, designed for the intermittency of the distributed generation. Both fast start as well as fast responding. And it burns typically natural gas. In fact, we've packaged at GE, we've packaged 10 megawatt lithium ion, 10 megawatts of lithium ion batteries with 50 megawatt thermal generation, natural gas thermal generation into a hybrid electric or gas hybrid turbine, electronic gas hybrid turbine, which is an integrated system. They can both satisfy instantaneous needs for frequency with the batteries, as well as any longer term needs with the turbine generator. Okay. Also can use bridging storage, right? Lithium ion batteries for energy storage. Now, this is an example of a grid edge controllers. So you've heard talk about controlling things at the edge of the grid. This is low-cost power electronics that is used to do continuous set point control at the edge of the grid for both voltage and reactive power. Call this low voltage network dynamic grid edge controller. I'll talk more about this. So that's why with power electronics, lower voltage power electronics now, when I talk with universities and industry in general, I said we need more interaction between the power electronic professors and graduate students and the power system analysis professors and graduate students, because we have new applications of power electronics in the grid. And I wrote an article in Power Electronics magazine, and this goes back, to 2013, because I had studied a feeder, a distribution feeder at San Diego Gas and Electric, and we got the voltage waveforms on that feeder. And I wanted to, this is a real situation here, going back that many years, of the impact of high penetration of rooftop solar PV on the distribution system. This particular feeder at the time, over 35% of the homes on that feeder had rooftop solar panels, over 35%. And these homes were beautiful homes along the Pacific Ocean that in the morning, there's a marine layer of fog from the ocean over the homes. And then as the morning went on, that fog would burn off. You should see the voltage waveforms on that feeder when all of a sudden 35% of the homes on the same feeder start generating because the fog had gone away and now all these PV panels see the sun. The voltage literally, it spiked tremendously and then oscillated as clouds, would go between the sun and the PV panels. The volatility of the voltage and reactive power on that feeder was unbelievable. I'd never seen anything like it before. The tap changer in the substation was operating before any home installed solar panels, was operating 5 to 10 times per day. Now this tap changer was operating well over 100 times per day. Remember now, these tap changers and substations are mechanical devices, right? 16 raised positions, 16 lower positions, a neutral position. Each mechanical change is 5/8% change in voltage, but they're not designed. These are mechanical controllers. They're not designed for that much duty cycle, okay? In San Diego on this feeder, the lifetime of that tap changer went from over 35 years to well less than 2 years. Well less than 2 years, okay? So my objective in writing this article was, you know, we need to think about new applications of power electronics with the future much more volatile grid. And 3 examples I talk about in the article is substation transformer online tap changers, low voltage network dynamic grid edge controllers, and increased capability from inverters, okay, smart inverters. And by the way, this article, you can search this article on the internet and find a link to it if you want to. The voltage waveforms from that feeder are included in the article. So we've learned a lot with our experience with renewables, but we also still have a number of impediments. You know, unobservable distributed generators that are behind the fence. We don't have any information from those. But some of the advances we've made are with thermal fleet, you know, higher response and quicker starts, and much better job doing forecasting. But I think bottom line is if anyone is going to, you know, think about putting a lot of distributed generation on the grid, make sure you model and study it. These are just some studies we've done at GE for different utilities with the impact of wind. Okay. Advanced distribution management system, the new SCADA system for distribution. This is the model for centralized control. It shows two inside the dashed lines, 2 parts to the platform. Basic SCADA server platform. And remember, SCADA means supervisory control and data acquisition. And then the powerful applications is set on top that optimize the distribution system in different ways. To the right is all the information from the substations and feeders that comes into the system. And then also the device control commands. So once we analyze the grid, then we optimize it through changing, through commands to change settings, right? So this is a group of applications that the operators use in real time. So we call these real-time DMS applications. They're continuously running. These are more analytical applications that run on demand. And this group are ancillary. These are additional applications that the utility would want to have on their DMS. Many of you are interested in a much deeper dive just on this subject. Another fellow and I, we teach a full day tutorial on this subject at IEEE PES general meetings and the T&D meeting. In the rescheduled T&D meeting, which will be in Chicago in October, I'm co-teaching the tutorial at that T&D in Chicago, and it's available to sign up and to take our one-day course. We go through each of the applications on the DMS in detail and do a much more in-depth discussion of the advanced distribution management system and distribution automation. So the concept today for utility, the goal is a digitized grid. And I'll finish up here and we'll have a chance for questions here in a few minutes. But you can't go from the bottom, which might be a manually operated grid, to the very top, which is a digital grid, in one step, right? Too much budget money would be needed. Too many people resources would be needed. So we put a roadmap together for the utility. Base level, there's manual control and legacy methods. Then we add SCADA, we add some trouble calls, we add smart meters, maybe some reclosers out on the distribution system. And now we have 28% lower customer minutes interrupted than the base level. Now we add automation and visualization, and we have 43% lower than the base. This is customer minutes interrupted. So much better resiliency, much better reliability with the system. Then we get to the digitally enabled, which is asset performance management, outage analytics, network optimization and utilization, much greater than 50% benefits. Okay, So you can stair step it with reasonable milestones and roadmaps, but every step should have significant benefits back to the utility. Another application of looking at things from a business point of view is a utility with 856 distribution circuits wants to improve their reliability. Well, it doesn't make sense to add automation to all 856 circuits. Let's look more deeply into these circuits, and we find that only 23% of all the circuits contributes 71% of the total outage minutes. So by investing in just 23% of the circuits, we can address almost 3/4 of all the outage minutes. Okay, this is a good example of really doing a deeper dive on, on the distribution system, and really making sure that we're getting the best bang for the buck. We're getting the best return for every dollar we spend. Okay. Now, in 2003, I wrote an article in IEEE Power and Energy magazine that introduced the concepts of operational, non-operational data to the industry, which now are somewhat industry standard. The operational, and the reason was we needed to get more benefits from our investment in microprocessor-based devices. We now call in the IEEE intelligent electronic device. The operational data is what we're used to. That's the data that goes to the control center for the operators, the SCADA operators. With the advent of microprocessor-based devices in the 80s, the 1980s, all of a sudden now we have available what we call non-operational data. This is both points and waveforms that not so much interested, there's not much interest by the operators, but I've found up to 25 to 30 different business groups in the utility that need this data. This could be maintenance information. This could be digitized waveforms for the disturbance analysis engineer. This could be power quality information for the power quality group. It's very valuable information, but it's not needed on a continuous basis like SCADA data. It's not a time series of information. This is on demand, and it's both points and files, like a sequence events report from a relay. So here I characterize the differences between operational and non-operational data with both data format. Operational is more real-time, non-operational is more historical. And operational, we typically use standard SCADA protocols to access that. With some of the data files out of IEDs, we may have a vendor-specific proprietary ASCII. But what we want to do is we want to leverage the Internet of Things, right? We want to, the fact that we're bringing together intelligent machines with big data and analytics and people at work, connecting all these together, there's tremendous opportunity here for savings, right? The Internet of Things. And on the left side here is the typical situation at most utilities today, with each group in the utility has its own systems, its own devices, and its own data repositories, okay? Very siloed. As a consultant, I'd find the same piece of data from the same relay in the substation in 3 different databases, the protection group, the maintenance group, and each of those groups would have accessed what was supposed to be a secure system in the substation to get that data. Why not have why not break down the silos of the groups, have a coordinated effort to say, let's get that piece of data out once across the firewalls into on the corporate network in a federated data mart here I'm showing on the right side of this slide, and have a holistic approach then to data management. And this is our goal on the right here, okay? Requires bringing together IT and OT and mapping all the data sources in the enterprise, mapping those to the data needs of not just the operators, but all the business groups in the utility. the end result on the left here is we have standard architectures. We're showing here a standard substation automation architecture with slave data concentrators and a master data concentrator. On the right is the ideal situation where in light blue, we have all the different data sources around the enterprise. And in green, we have all the different users in the utility, all the different business groups. They now have all the data they need from all the data sources in the enterprise, which means that they can provide the maximum benefits to the utility. And so the utility then is getting they're realizing all the benefits that they should realize from their investment in all these data sources. Now, this slide here is where we are in a journey to digital transformation. This is exciting to me because for many years we were reactive, right? We waited till something failed and then we try to fix it. And we said, well, let's be more responsive. Let's be responsive here, have better situational awareness, location with automated restoration and crew productivity. Now we're more at predictive in the middle here. What health do we need from the asset? What analytics do we need to predict, possible failure mode occurring? Many people in the industry think predictive is the last step, but I'm showing here we're only halfway to where we can be. What we're doing is now we're applying machine learning, artificial intelligence, we're hiring data scientists, and the concept of the digital twin, and we're moving now from predictive to prescriptive and eventually to autonomous. Autonomous would be self-healing, self-provisioning, and extensive autonomous operation with limited human intervention. This is exciting to me. This is why a number of us spent a couple of years when we wrote the book I mentioned, Big Data Application and Power Systems. We're showing a lot of different examples of how we can apply this to different parts of the grid, okay? So standards are extremely important. On the left side here, I'm showing what we developed in 2010, which is a smart grid conceptual reference model. I chaired the board from 2010 to 2015 of the smart grid interoperability panel. 25 of us were responsible for coordinating all the smart grid standards work for the U.S. government, particularly for NIST, the National Institute of Standards and Technology. And we were funded by the stimulus funds of 2009. One of the things we did, though, was we looked at the over 100 smart grid standards from IEEE, the over 100 smart grid standards from IEC, and we said we have to help the industry here. What small group of those standards are the most important? And these standards here, this is really the foundational set of standards for smart grid, okay? You really only have to look at these 16 standards. You don't have to worry about the 100 IEEE, the 100 IEC. These 16 are the most critical standards for smart grid, okay? And what's cool is that in the top here, worldwide, now there's one standard, one worldwide standard for any control center to talk to any other control center to exchange information. And that's what we call ICCP. The control center of the field worldwide, there's really two standards. For North America, we use DNP3, which is now IEEE 1815, or European suppliers will use 870-5, 101, and 104. 101 for serial, 104 for network communications. Within the field, again, there's really just two. In North America, we still use a lot of DNP3, but worldwide, the transitioning to IEC 61850 as the global standard, okay? So let me finish with a few slides. We, after 18 months of deploying smart grid projects, initially we captured our lessons learned. First lesson we learned was that integrated solution has a lot of technology components, and if any one of those is not mature, it has some weaknesses, it will bring the whole solution down. Same thing with a chain. The chain is only as strong as its weakest link, right? So we found the component technology was not as mature initially as advertised. And that's why we had to do some field re-engineering or upgrading. But the main thing was you need to take these solutions out to the field, because that's, you can test them in the factory, but you really, the ultimate test is in the field. Second is we learned, we experienced how important standards were. Integration, interoperability, compliance to the same set of standards. Third is testing. You can't test enough in the factory. It's much easier to test in the factory than it is in the field. But what we really learned was we need to do end-to-end testing, right? These solutions go from the component in the substation up to the office and the control center. Test end to end, okay? You have to coordinate multiple suppliers because these solutions have equipment from different vendors. Utilities, the challenge is coordinating these multiple suppliers within each utility. The other challenge is, and we really learned this too, was it's important not just to have your top technical and engineering people, but you have to have your top project management people. We could supply a utility, a G, the best technology, have the best engineering team at the utility, but if we have a weak project manager, the project could be unsuccessful. So each project manager is a very, very important part of the project. And they need to have not only the responsibility for the project, but multidiscipline authority. They need to have authority within their company over all the disciplines, planning, maintenance, engineering, power quality. They need to have authority over all the groups that are involved in the project. There needs to be a program management office, a PMO, with consistent project management guidelines and rules. In the middle of the slide here is really what's, a very important point is each utility need to build an A team of the very best project and technical members. There will be challenges to collectively solve, particularly in the field. And just having the best technical members isn't enough. You need, as I said, top project people too. Each utility should have its own smart grid strategy, which is holistic across the whole, not just each group, but across the whole utility. And then those utilities have a corporate steering committee. So any new idea for a project has to be aligned with the overall smart grid strategy. And then very last slide here. One thing we found with some of the initial smart grid projects was that the end use customer is an important part of smart grid, major stakeholder, and you have to engage customers. Many of the initial smart grid projects were smart metering projects, right? Putting smart meters on a smart meter on someone's home without talking to them and engaging them is asking for disaster, okay, which happened with some of the pioneering utilities. So customer engagement is very important. 10 years ago, we formed a new organization in the industry called the Smart Energy Consumer Collaborative. I'm a founding board member, and GE is a founding member, and I've been active in that for all 10 years. This is a group with over 100 members, many utilities, and we focus just on the end use customer part of smart grid, okay, with research and education. And then I'll finish here with how important use cases are. Anything that you want to do at the utility with respect to grid modernization, we really need to define it with a use case, right? Describe its scenario, define the benefits, who's involved, in other words, the actors, functional requirements, business rules and assumptions. And that really helps us understand what groups in the utility should be involved, what training is needed, and what engagement with the vendors, and what kind of a team do we need to put together to be successful. Okay, I'll end here. That's the last slide, and would love to have questions and to hear from all of you, comments and questions. Thank you.
Thank you, John. I think this was a very good presentation for us to look at all the technologies and to look at the roadmap of the different technologies and information within it. At this point, we are open to questions. So, Rafael and Mustaq, if there are any questions that have been sent in the chat, please, please know.
Yes. I have questions. So the first question is, how would you envisage availability of data to provide prescriptive or autonomous features? It appears that the data collection is not uniform, and at this moment by the distribution grid operators.
So I think the question was envisioning autonomous operation.
Yes.
Okay. Um, so you know, in the one-day tutorial we'll do on distribution automation and ADMS, we'll go over this in a lot more detail with examples. But we have today logic, you know, we can put on a distribution system called fault detection, isolation, restoration, or some people call it fault location, isolation, service restoration, which is FLISR, right? And what we can do is we can put the logic, could be at the control center, it could be in the substation, that detects the fault, locates the fault, and then obviously the first step is to isolate the fault. So you know, you need to have a certain number of switches on your feeder to do this logic. So that's why one of the blue boxes I had in the roadmap was a lot of the switches, right? So we open up switches on either side of the fault. That way we isolate it. Then we do upstream restoration and downstream restoration, okay? So utilities can implement this logic in 3 different ways. You can implement the logic, have it give you recommendations, but a human is always in the loop to you know, to implement the recommendations. That's called the manual way of control. Second would be semi-automatic. A lot of utilities are semi-automatic where upstream restoration is done automatically, but they still keep a human in the loop for downstream. Upstream is very straightforward. Downstream can be more complicated if there's a number of normally open tie switches where the feeders can shift load segments from feeder to feeder and substation to substation. Fully automatic, though, is where upstream and downstream restoration is all done automatically, which means from the time of fault occurring to a time when only the faulted segment has the outage can be less than 2 minutes, 1 to 2 minutes. The reason that's important is that to take the human out of the loop is each utility is judged, the reliability is judged based on very important reliability indices called SAIDI and SAIFI, right? SAIDI has to do with the duration of the outage, and SAIFI, the F, is frequency of outages greater than 5 minutes. And if you can have the upstream and downstream customers restored in less than 5 minutes, that's the best possible situation with system reliability. And that's what the goal of most utilities is today. So when you keep a human in the loop, you're going to be greater than 5 minutes, right? Mm-hmm. The reliability is not going to be nearly as good as it would be if you close the loop, take the human out of the loop, and pull it and do closed loop control. So it can be done. Many utilities are doing it today, and it works. You know, you put the logic out there and test it first in manual mode to make sure all the recommendations make sense. We fine tune the logic. When we have full confidence in the logic, then we close the loop on it. First, we may close the loop semi-automatic, just doing upstream restoration only, human in the loop still at downstream, but eventually we'll want to do fully automatic. and do both upstream and downstream restoration automatically.
Thank you. And the other question is 23% of all 856 circuits are causing the outage. Which are the most important circuits that cause this outage?
You know, it's hard to it's hard to generalize because it wouldn't be the same with each utility. Okay, so each utility typically each utility has a list of their what we call their worst performing circuits, like the worst 10 circuits, the worst 15 circuits based on reliability. The reasons for this could be several things. One would be it's old overhead service. It's not underground. It's old overhead service, which has aging equipment. It could be that it's in an area that has a lot of lightning strikes. Maybe in Florida. It could be it could be an area where the vegetation grows very quickly, right? And the vegetation isn't managed or trimmed as frequently as it should be. And when it gets windy, the wind blows a tree branch or vegetation into the conductor and causes an outage. Okay, so it could be a number of different things. That's why we really we have to study that with each utility and find out, what is the reason? How can we address that? But I think, what I was showing with that example was you don't have to assume that you need to spend money and automate all 800 circuits. Okay? Let's study each of those circuits and find out, which ones contribute the most to the outage minutes, and then let's focus on those first. Okay.
Thank you very much.
I have received one question. Thank you very much for the presentation. I have heard that there are certain unease among the power engineer about using deep learning for power system control due to the limited explainability of the internal working of the DL algorithms. Is the unease true? How important will explainability be for the increasing use of DL algorithm in the power system monitoring and control?
Yeah, that's a good question. I would say, extremely important. We, every year we have a CGRE U.S. Grid of the Future conference. This year it'll be hosted by National Grid in the first week of November. And I usually receive 100 papers on very key industry topics. And I typically get a lot of papers on machine learning, artificial intelligence, deep learning, the application to asset performance management, okay, particularly with transformers and circuit breakers, the use of the digital twin, so I would say if there's one area that is of great interest to me, it's data science. Okay, we're hiring data scientists at GE that we had never done that before. Our GE digital business, utilities are hiring data scientists that they had never done before. Okay, the challenge is that a good data scientist typically doesn't have knowledge of the power system. If you find a data scientist that has some experience and knowledge of domain expertise with power system, that's an unbelievable combination today, which is rare. But we're taking data scientists and applying them, with deep learning, artificial intelligence, machine learning, artificial intelligence. And applying one of the first applications was with asset management. And there's so many benefits of this, because as I mentioned earlier, you can extend the life of an asset by doing this. You can prevent catastrophic failure. If I have a transformer in a substation with a catastrophic failure, I not only lose the transformer, I lose the entire substation, right? You know, when it explodes, you have pieces of metal flying around the substation that destroy everything else. Then I have the oil from the transfer. I have a hazardous material, a hazmat situation. I mean, it's a complete mess. If I can prevent catastrophic failures, and if I can see a trend immediately towards a problem, right? I can address that right away. And you know, for $1 million transformer, I may spend what, $40,000 on monitoring and diagnostic equipment. Think of, for a very small investment compared to the cost of the asset itself, you know, I have enough health information that I can detect almost all the possible failure modes of that asset. And that's why I put this slide back up here. Instead of reactive, I can be predictive, right? I can predict what's going to happen and take care of it. So I would say, you know, data science today, deep learning, and the application to asset management is huge. It's big, and the business case is extremely strong. We have industry conferences that are just on the subject. I give keynote talks every year at TechCon, TECHCON. The whole conference is on asset management. You know, so this is a big area today, and you know, I would say, you know, the more we know about these concepts, and then the more we can apply these to real world power system grid type situations like asset management. Uh, in every situation, the business case is very strong.
I have one more question from our participants. Could you please provide more insights on the difference between digital twin and IoTs? And what would be the penetration of digital twin in today's systems and future equipment? Is it a hype, or there is more reality in it?
No, I could show you examples of digital twins today that at both industrial customers and utility customers. They're in use today. Think of it's well, Internet of Things is kind of up above, right? It's taking intelligent machines with big data and analytics and connecting them with people, no matter where the people are, in any way we can connect for a totally integrated operation. But if we do a deeper dive into asset management, I guess one analogy would be, think of you know, when we look at SCADA systems, right, and we apply SCADA to generation and transmission, we have what we call an EMS, energy management system. We apply SCADA to the distribution system, we have what we call ADMS, right, advanced distribution management system. Now, for many utilities, if you want to test a new application, if you want to test, you know, a switching scenario, if you want to do some testing, you don't want to do the testing on the online system, right? Because that's the system that's monitoring and controlling the grid every second of the day, and you don't want to mess with that. So many utilities have a dispatcher training simulator or an operator training simulator that's a duplicate of their online system, right? That's typical with an EMS, and it's much more typical today with ADMS. Okay, it's a duplicate set of hardware and software, and I can snapshot the real-time database with my dispatcher training simulator, and I can test different things, right, without affecting the online system. Think of the digital twin as kind of like a dispatcher training simulator, but for an asset, right? For a transformer, for a circuit breaker. So I first know the physics of that asset. You know, how does a transformer operate? What's the transfer function within that asset? And then I look at all the possible health information that I can gain from that asset. And then I put the two together and I have a digital twin. Digital meaning it's digitized, right? I have a lot of data, but it's a twin because it's a copy of the asset itself, because I've used the physics of that asset. Then I can use that to test a lot of different scenarios, applications. You know, am I detecting all the possible failure modes of the asset? Do I have enough health information? You know, for a transformer, do I have bushing monitor information? Typically, if I just focus on the main tank and maybe the tap changer tank, I may be missing the bushing information, which could cause the transformer to fail, right? So I have separate bushing monitors that I can couple in to the digital twin, right? So it's a good way to make sure I have a complete, you know, solution to test different things without affecting the actual asset that's online and in operation. And it's real. It's in use today. You could talk to our, for instance, the G, you could talk to our G digital business, and they could give you examples at many different industrial organizations and utility organizations where digital twins are being used.
Thank you.
I think if there are no questions, we probably should be at the end of our event in that case. Rafael and Mustaq, are there any other questions from our participants?
No, there is no any question on my side.
Yeah, no.
All right. I'd like to thank John for this deeply insightful presentation and a well laid out thought process into what could the future look like, with a lot of details into what the state of the art is, where we are going, and how we're going towards that direction. I think this was a presentation from where I learned a lot personally. So thank you again, John, and thank you to everyone for joining in and for all the insightful questions. John, over to you for the last few minutes before we drop out.
Yeah, well, I've been doing distinguished lectures for IEEE Power and Energy Society for over 20 years. It's been 21 years, and never had a COVID situation, right? So it's fun today trying to do these virtually. You know, where normally I'd be you in person, which you know I wish I could be, but at least we can, you know, we can have a distinguished lecture virtual. The one thing that I want to leave you with, though, is I talked about a lot of different topics. I have a lot of additional information, you know, over 150 papers and articles, and you know, involved with 5 books. If anyone would like more information about any topic, you know, if you want more details about something that I mentioned, let me know, because I probably have a number of articles and papers that I've done or that others have done that I could send you to help you with the need for more information. So, you know, don't hold back. Let me know, and I probably have a lot of additional resources that I could provide you. Okay, and just to end, you know, I just want to thank you for the opportunity today, and if at any time in the future you know you want to, you know, we could do, obviously we could do a live distinguished lecture at some point when we can in the future, but if you'd like to do another virtual one, just let me know. I've got a number of different topics that we, both technical and career development type topics that we could do. So just let me know. Thanks again for the opportunity today. I appreciate it.
Sounds good, John. Sounds good. I think we would be certainly happy to host you again in the near future. Uh,